The first one is from Li Jin. He's from University of Birmingham. He is from the Department of Mechanical Engineering, School of Engineering, University of Birmingham. His main research interest is application of multi-objective optimization to vehicle powertrains and vehicle dynamics. His speaking topic is digital twin-assisted parallel learning for fuzzy logic-based engine-powered hybrid propulsion control system. So, welcome, Li Jin.
Hey everyone, my name is Jay Li, currently a research fellow working at Vehicle and Engine Technology Center, University of Birmingham. It is a great honor for me to be invited as a speaker to present our current work. Today, my topic is digital twin assist parallel learning for fuzzy logic-based engine-powered hybrid propulsion control system. So my presentation includes 8 parts, which are team profiles, background, research objects, proposed solution, experimental setup, result and discussion, conclusion, and the topic extension will be the end. Vehicle and Engine Technology Center is led by Professor Hongming Xu. He has 6 years of industry experience with Jaguar Land Rover and Ford, over 400 journals and conference publications in engine flow, combustion, emissions, transit operation control, and hybrid electric vehicle development. He is also a fellow of SAE and IMACE. CASE-V team is the biggest research group in this center, which means connected and autonomous systems for electrified vehicles. It aims to improve and level up transport across the world by making everyday journeys greener, safer, more flexible, and more reliable. There are 2 academic staff, Professor Hugh Williams and Professor Mike Richardson, 2 research staff, Dr. Zhou and me, and 7 PhD and several exchange students. Let's back to the research. For hybrid electric vehicles, developing optimal energy management system is critical to achieving the best performance and energy efficiency. So the fuzzy logic approach is a well-known heuristic strategy, and it plays an essential role in handling measurement noise and component variability through its adaptive nature. As an emergent technology, digital twin can integrate the physical and the virtual data throughout the development of EMS, which leads to a huge volume of data that can be processed by advanced analytics. So hybrid propulsion system, which is supervised by the vehicle controller, includes a gasoline engine, an integrated starter generator, a transmotor, and it's powered by a combination of fuel and electricity. As shown in this figure, here we choose a transmotor, that is an electric motor with a float stator. The ISE drive and the transmotor drive are combined by combining them in series, so that their speeds are added. They can be decomposed as well via the operation of clutch and the locks. The main parameters are summarized here in the table 1. In order to relationally assign the vehicle's power demand, which has a corresponding torque demand that can be measured at the reducer input, to the 3 machines, it is paired with the state of charge of the battery pack to make up the input to the fuzzy logic-based supervisory control system. That choose between the 2 modes of pure electric traction and fuzzy logic-based tractions. The expression goes as these two equations. The electric traction system has the capacity to completely satisfy the torque demand, enabling deactivation of the ICE and ISG in the electric mode. In the fuzzy logic control mode, fuzzy logic controllers are used to perform energy management. This structure supplies power to propel the vehicle while maintaining the battery pack's state of charge between the safe limits. The design of the fuzzy logic rules is described in Table 2. The concept of the proposed digital twins assist parallel learning mechanisms comprise one controller's DT. So here there is virtual controllers and the two main modules. One is parallel learning, another is real-time evaluation. In the parallel learning module, the virtual controller with the same fuzzy logic structure were adopted and online trained by the intelligent swarm optimizer. In the real-time evaluation module, there is an evaluator that competitively assesses the two controllers, and its assessment result decides whether controller parameters of the virtual controllers are synchronized to the real controllers. During the real-world driving, if the better membership function scatter parameters in the virtual controllers are detected, the evaluator will pass the new membership function parameters to the real controller. So to simplify the implementation of optimization algorithms, it is assumed here that the parameter AM, BL, and AHCL, BH, and CM are fixed for each input and output. In this way, 24 scatter parameters of the membership functions needs to be optimized. For each iteration of algorithm optimization, it is necessary to check these constraints as shown in this the equation in left-hand side. So this paper considers two principal targets. The first is the overall liquid fuel consumption, and another is the battery pack's state of charge at the end of the test. To convert these two objectives into one, enabling the swarm-based optimization algorithm, in this present work, the multiple objective optimization is formulated by using the weighted sum method. And also a computational algorithm, Charles enhanced accelerate particle swarm optimization, inspired by the animal swarms. Here is applied as an online optimizer for the virtual controller. So the figure at the left-hand side investigates the averaged value of cost function with different orders of the penalty during real-world driving with an initial SOC values of 0.2. The cost function of the both objectives are scaled to the same ranges of 0 to 1, with the weights fixed at 0.5. So compared to another investigate orders, the quadratic penalties J2 gives the only positive differential related to the J1. In the real-time driving, the cost functions of the real controller are considered as a learning target to motivate another. At each time step, the proposed mechanism will calculate the cost functions of both controllers if the current state meets the following switch conditions. The proposed mechanism will take the action to pass the new membership function scatter parameters used in the virtual controllers to the real one. Otherwise, the mechanism will continue to explore the scatter parameters, searching for better field-saving performance for the next time step. Experiment setup includes two main processes. One is data collection of driving profile. In this study, 5 human drivers with different driving experience are involved to drive on a driving simulator under the different traffic types like urban or highway. These signals of driving actions will interact with the IPG car maker equipped with the studied hybrid powertrain. And finally, the driving profile will be generated. And this will be used as input reference in the hardware-in-the-loop test system to validate its real-time performance. From the result of the top sub-figure, the virtual controller is continually updated by the proposed DTPL, and transfer work of the new membership functions parameters occurs frequently at protruding spikes, which are caused by the dramatic changes in human driving behaviors. The bottom sub-figures dissects output surface evaluation process between the two fuzzy logic controllers. It can be seen that the DTPL mechanism will abandon a relatively smooth output surface used for most driving scenarios and replace the two aggressive ones for targeting higher fuel economy. Here, the fuzzy logic-based hybrid propulsion system with the proposed mechanism is further compared with the conventional one. And the fuel consumption under the fuzzy logic-based control system is significantly lower than the conventional one, while maintaining the higher SOC value. Boosted by the DTPL, the ICE initially attempts to compensates for the total power demand to avoid the potential danger of a rapid drop in the battery package's state of charge. The ISG maintains a higher workload compared to that supervised by the conventional fuzzy logic-based control system. So here is the conclusion. At the end, the conclusion will be drawn from the investigation. So the first point is, assisted by the DT technology, the proposed mechanism has demonstrated its abilities to ensure the effectiveness of the fuzzy logic-based control system to adapt it to the changes of the driving behaviors. So the second point is the fuzzy logic-based control system driven by the proposed mechanism can significantly improve the fuel consumption under the different initial SOC conditions. The last one is this system can reduce the fuel consumptions over the testing real-world cycles up to 15% from the CDCS-based and also 12% from the conventional fuzzy logic-based systems. There is another one of our most current research on the basis of the DT's concept. The mainstream control optimization schemes include the model-free scheme that is, or the algorithm interacts directly with the real vehicle systems, and the model-based scheme that is the algorithm interacts purely with an empirical model. The former use a heavy experimental efforts in exchange for the better system performance. The latter requires the expert experience on empirical model development. The proposed DT assist EMS optimization scheme, as enumerated in these figures, is an interactive form of the model-free and model-based scheme. By introducing the confident factors, this proposed the SSPA use the fused data of physical measured and the virtual simulated vehicles performances. That requires the less R&D cost than the model-free method, and more than 44% energy can be saved during the R&D process, and 4.8% energy can be further saved by the optimized system over the WLTP cycle. So, thank you for attention. Hope our work can give you some inspiration. Thank you.
Okay, thank you, Professor Lee. Would you so kind to open the camera? Thank you.
Hello.
Thank you. Hey,
Hello, can you hear me?
hey, is there anyone have a questions? Okay, I have a question. Why not use DP as a benchmark for the comparison?
Sorry, can you repeat again?
In your paper, you did many. You have used many algorithms. So why not use DP as a benchmark for the comparison?
All right. So yeah, you get a good question. Yes, yeah, we use the DT, the digital twins as because the digital twin is currently an emerging technology that can, yeah, as I said in the PowerPoint, can integrate the data from the cyber and also the physical sites. So in this work, the DT can just used one of the virtual controller, but that one is also like the we can say like the shadow models of the fuzzy logic controllers. So basically, is a fuzzy logic that is a benchmark in this study. And also, the benchmark is fixed with a fixed rule, but we want to do is to activate that rule to like the dynamic. So in the real world driving, so that rules can be upgraded to adapted to the various driving conditions. So this is the main idea in our research. So yeah.
Okay, thank you. Because of the time, thank you.